Welcome to the 27th class meeting of EECE341, Introduction to Communication Systems. The most important announcement is the final exam. As I told you already, it will be taken on Friday, December 20th, from 7 p.m. to 10 p.m. at the next class meeting room or this class meeting room. I'm not sure this one will be available. I reserved 104, but I prefer this 102. About the voluntary project, some of you asked some specific topics, but I said no. So please check your email. Sending just the topic is not enough. You must get my approval. Especially one of the students who sent me an email. The topic was I believe was not good because it didn't make sense. So please check your mailbox whether you received my rejection email or not. About the messages throughout this course: simplify and visualize, existence and uniqueness, ask why not, what if, great inventions, and also two buildings, conceptual, for the electrical engineering. There are not much to correct and clarify this time. And we were almost at the end of chapter 5. So the chapter 5, even though is entitled as baseband digital transmission, it has the carrier modulation. And I combined that with chapter 9 material and cover it today. I will cover it very quickly because most of the topics will be repeated in the Introduction to Digital Communications course offered in the spring 25. As I told you, I will have more emphasis on this information theory and coding. So we are going to use chapter 1 material again because at the end of chapter 1, I put some slides for information theory but didn't cover at that time. So as you see here, okay, it is not synchronized yet, but anyway, so we will use that one. Let me review last class meeting. So in the last class meeting, we studied what is a matched filter, and its definition is not, how to say that, not clear at this moment, because even researchers has different definitions for matched filters. But what you need to remember is this figure. Just a second. Is it? Yeah. So you have signal y of t, that is the summation of the known signal, actually, s of t, and noise n of t. And here, n could be a colored noise, but the simplest definition of a matched filter assumes it's a white noise. So simplified definition assumes n of t is white noise. And our task is this one. So given the signal y of t, we want to design some filter with impulse response h of t. And we want to sample this output at time t0. And after sampling, we have a scalar valued signal component plus noise component. Here we define the signal to noise ratio or signal to noise power ratio. Here, let me use Let me use the absolute value sign. So here, be careful. This line means that S of t convolved with H of t is evaluated or sampled at time t0. So you have a scalar, and that could be complex valued depending on the definition. And we take the magnitude square of it. And here goes the noise power. Again, sampled at t0. And we take the magnitude square and take the expectation. So the numerator is the magnitude scale of the sampled desired signal part, and the denominator is the statistical average of the noise component sampled at the same time instant t0. And here, H matched filter of t is defined as the argument that maximizes this SNR. Of course, as you learned in introductory optimization theory, I heard that that is one of the most popular course for the undergraduate postdoc students. This problem is a little bit ill-posed in terms, in the sense that we have infinitely many solutions if the solution exists, because any constant multiple of the optimal solution still maximizes SNR. So the conclusion is that we have some constant k times S of t0 minus t conjugate. So this is the theorem. Okay. So matched filter maximizes. So this given the observation model. This is the definition. And theorem says that the matched filter is what? The time reversed complex conjugate of the desired component properly delayed. Got it? So simplified solution is that if we set for convenience t0 equals 0, then what do we have? The matched filter is what? Proportional to the time reversed complex conjugate of the desired component. Based on that, we may define so-called the square root Nyquist pulse. And square root Nyquist pulse satisfies this condition. If P of t is a square root Nyquist pulse for the sampling symbol transmission rate 1 over capital T and possible sampling offset 0, then this one, let's say this is Q of t, satisfies what? Satisfies Nyquist condition for 0 ISI. So the folded spectrum of Q of t. Q of t is called the time autocorrelation function of P of t. Is what? Is a Nyquist pulse. So Q is a Nyquist pulse, and P is a square root Nyquist pulse. In other words, the magnitude square of the square root Nyquist pulse shifted by integer multiples of the symbol rate becomes a constant function in the frequency domain. And example is what? Example is a rectangular pulse. So you have a rectangular pulse with width t, or to make everything simple, let's have P of t centered at the origin. And let me ask you, P of t is a Nyquist pulse? P of t is a Nyquist pulse for the symbol rate 1 over capital T? Yes, it is, right? And another question, P of t is a square root Nyquist pulse for the symbol rate 1 over t? Yes, it is. So there exists some interesting class of pulses that is a Nyquist pulse at the same time a square root Nyquist pulse. And usually time-limited pulses satisfy this one, that is span capital T. But let's little bit change our question. So given the set of band-limited signals, can we have a pulse that is a Nyquist pulse and at the same time square root Nyquist pulse? Actually, yes, you have. Which one? Sync pulse. So sync pulse is a strictly band-limited Nyquist pulse for, it can be for the transmission rate 1 over capital T and also the square root Nyquist pulse. So if this is sync square with zero touching, first the zero touching points plus minus 1 over T. And if you fold this spectrum, then it becomes constant. Interestingly, if you have a Nyquist, just the sync pulse, and if you fold, you again have the constant. But that summation is a little bit tricky, actually, that summation. So people rarely claims to use sync pulse. Sync pulse does not behave well in the sense that it does not give us an absolutely summable sequence when we sample. Anyway, so last time we studied raised cosine pulse. So there exists corresponding square root raised cosine pulse. And this is the pulse that is very popular in wireless communications. For example, in your 3G WCDMA, the spectrum is actually raised cosine spectrum. And the pulse is actually square root Nyquist pulse with roll-off factor 22%. This design of a square root Nyquist, a square root raised cosine pulse is very standardized. So it can be well designed with, it can be well approximated with finite number of taps, something like that. Anyway, the next topic was synchronization. Some of you are taking the lab course for communication and networks, and probably today you really need a rough synchronization to do your task. So there are many levels, different synchronizations, as you did in your homework. Sometimes we need phase synchronization, sometimes we need carrier frequency synchronization, sometimes some kind of timing such as symbol level, frame level, sometimes some other name like slot level and some other things. And the order of synchronization varies. This is one of the most important messages for you. The order of synchronization sometimes must be changed depending on your channel situation. Never think in this way. After this synchronization, that. No. Okay? Sometimes you have to change the order of synchronization, especially when you have a very low signal to noise ratio. If you first try to synchronize or recover your carrier frequency, you will highly likely fail. Okay? So be careful. Synchronization itself is a very important and very big topic in digital communications. So in the advanced communications course, this big synchronization you will see in the textbook of a course. Okay, here goes the preview of today's material. So we will cover the last section, that is carrier modulation of baseband digital signals, even though our chapter is all about baseband digital signals. So the first slide is left blank, and let me ask you about these terms. So you've heard some terms like key and keying. When I talk to you about the telegraph or telegram. Key is translated into a Korean as 전건, and probably as you've seen, it looks like this. So if you push, then this gap opens, and if you release, then it closes, something like that. So that you can on off the circuit, and this on off action generates the Morse code. And this is called the key. And if you push the key, it is called keying. And this term is kind of stuck in the communications society. So afterwards, some abrupt change in something is called keying, especially when that keying is performed to send some digital message. So suppose you have a local oscillator that generates a carrier. Where the amplitude and the phase deviation fixed, and you have carrier frequency FC. Now somehow you build a system that accepts your message and generates some signal that changes possibly the amplitude and possibly the phase deviation. This is called what? This is called modulator, because it changes amplitude or phase of the carrier. So carrier is modulated by this modulator to convey the message signal. And this message signal could be an analog form or digital form. Now, let's restrict this to digital form. Among many digital formats, let's assume that M of t is something like line-coded signal, but not necessarily the symbol takes 1 or -1. It could take other values. For example, this could be a symbol taking 1 of 4 values. In this case, this is called 4 pulse amplitude modulation, 4 PAM. You can have -1, 1. In that case, it is called 2 PAM, but it is more called binary phase shift keying. Here, PSK is phase shift keying and contains the word keying here. And you must interpret this as abrupt change. So in BPSK, this is binary, you have abrupt change in phase of the carrier to put your message. And you may say that, what is this A of n in the set of -1 and 1 is related to phase shift in the carrier? This is a little bit complicated to understand, but I already explained we have some equivalence like this. Suppose your modulated signal here is in this form. Got it? So here, if an equals -1, you have, sorry, not this one. B must be, yeah. Let me see. Okay, so you have bit, and here pi. Okay, so in BPSK, your B of n is either 0 or 1. A of n is either 1 or -1. Got it? Am I right? Yeah, I believe so. 0, 0. Yeah. So if your symbol B equals 0, you do not add any phase. If your symbol B equals B sub n equals 1, you add pi radian. Then what happens? And this change in phase may occur every capital T. So you have some signal like this. So here, you see, you have a sine pulse that continues up to time capital T. And if the symbol B does not change, then it must continue. However, here we have the symbol change it. So you have pi radian flip that corresponds to multiplying -1. So you can show like this. So here, in the argument of cosine function, we have abrupt phase shift by pi or 0 at every t. And after you manipulate this one, possibly using the complex envelope form, you have what? Here, a baseband signal times carry. Okay? Fill up this part. Got it? And it may appear in the final exam and something similar. So now, what is this one? This is what we learned in this chapter 5, digital baseband signal. So it seems that phase shift keying, especially here, binary phase shift keying, can be interpreted in two ways. You really shift phase of the carrier, or you multiply or mix the RF carrier with a digital baseband signal. And this is kind of natural because every real valued bandpass signal, x of t, can be written in what? In this form. Here, this is a complex baseband signal and called complex envelope. So, we can rewrite it this way. Again, digital baseband signal appears here. Now, let's generalize this one a little bit. By the way, in the abrupt change, P of t was what? Here, P of t was a rectangular pulse, right? And after we change in this form, we've already learned, but not derived, the power spectral density is what? Sinc square located in plus Fc and negative Fc, which is not good. So people generalize first, change P of t from a rectangular pulse that has sinc square spectrum to something good, like square root raised cosine pulse. Right? In that case, you don't have abrupt 0 pi radian change in carrier. However, we still call this as binary phase shift keying in modern textbooks. In the old textbooks, whenever we say phase shift keying, you can assume that the baseband digital signal has what? Rectangular pulse. But however, people already have generalized that. So now what we say is this one. When we have non-rectangular pulse, this is called what? If this is negative 1, 1, and this is called BPSK symbol constellation. So now this symbol is called BPSK symbol. Precisely speaking, BPSK is related with what? Phase shift of carrier. But after we divide the effect of phase shift as the modulation symbols effect and the pulse shapes effect, we call the symbol as modulation symbol, especially here, BPSK symbol. So this is, in general, a modulation symbol. So as you see here, the terminologies currently being used in digital communications have been evolving. Long ago, the name was more restrictive, and now it's more general, or vice versa. So whenever you communicate, probably you remember that Babel Tower I've shown in the first class meeting. You have to agree with your colleagues about the definition of terminology. Otherwise, there will be a lot of confusion. So the first one was change the pulse, and second one is very amazing. Now, A of n, since this can be a complex, could be complex signal, now may be generalized to something like this. So on the complex plane, here you have a unit circle, and these 4 points could be now transmitted using complex digital baseband signal that modulates the carrier. That is now called QPSK. Q means quadri, means 4, PSK, so quadri-phase shift keying. So 4 PSK sometimes. And in 4PSK, if you still have P of T, a rectangular pulse, then if you look at the real valued bandpass signal at every capital T, your carrier may change the phase whose amount is an integer multiple of pi over 2, because this is pi over 2. Sometimes QPSK modulation symbol has constellation points not on the real and imaginary axis, but on these 4 points. It depends on your choice. Anyway, now this is about phase shift keying. What about amplitude shift keying? So in amplitude shift keying, actually we've already seen. This is amplitude shift keying. So amplitude of carrier can take 4 values. And interestingly, if you have a negative signs, actually it corresponds to shift phase by pi. And here magnitude is 3, 3, but they have different phase. So it appears that we may combine amplitude shift keying and phase shift keying at the same time. That is called quadrature amplitude modulation. So BPSK, ASK, and QAM. Here in QAM, we may have modulation symbols, something like this. So A of n is a member or point in this set of complex numbers. To make everything simple, let's say this is 3, 1, -1, -3, and same for the imaginary axis. In this case, it is called 16 quadrature amplitude modulation. Of course, there are many different digital modulation symbols. There is something like BPSK used for satellite communications, digital satellite communications, and there are a lot of different modulation symbol constellations. So one of the most popular modulation scheme generates the signal, something like this. Here, now A of n can be a complex modulation symbol. That's why you see again and again some complex valued symbols in digital communication. However, be careful. If we want to do real valued baseband signaling, then complex valued constellations cannot be used because there is no carrier. So be careful. These complex valued constellation modulation symbols are for real valued bandpass signaling. However, there could be some trick. For example, suppose you are going to use some baseband spectrum from, for example, 10 megahertz to -10 megahertz. And you've measured your channel response, and your channel gain looks like this. So it does not pass the DC component. So you have a channel that is well modeled as a real valued baseband LTI system. So this is channel. And you want to design some digital transmitter and receiver. And you may say that, this channel is too bad, which it has a kind of notch filter shaped response. What do I do? And there is a trick. What you do is something like this. So you design a real valued bandpass signal that occupies this spectrum. So what you do is that you choose this one around here as carrier. And then you may have real valued bandpass signal, right? That's possible. And to do this, especially for telephone modems, long ago, people devised a method that is very similar to OFDM. But OFDM generates complex valued signal in baseband. So what they did was to carefully choose redundancy in the subcarrier symbols so that you still have what? Conjugate symmetry, which guarantees realness of your signal in time domain. And that made all the trick work. So if you have a chance to read some material about baseband signaling, for example, you may have interest in power line communication. In that case, you have to design some modulation scheme that does not have good, that should not have a DC component or with very small DC component. In that case, you can still do real valued bandpass signaling by properly choosing the carrier, or even you can do something similar to OFDM, but keeping the conjugate symmetry of your signal in the frequency domain. But anyway, so let me go back to the subsection title. Here, this section is about the relation between baseband digital signal and carrier modulation. Here, most of the signals were assumed real baseband. But now, here, this baseband signal can be complex baseband signal, as you've seen here. Got it? So this is a baseband signal. And even if P is real, AN is complex, then signal becomes complex valued. There are other modulation schemes called frequency shift keying. And this is a little bit different from the so-called linear modulation. This is, in general, nonlinear modulation. However, this FSK and previous linear modulation has actually intersection. But anyway, FSK means that your carrier has sudden shift in frequency. So as you see here, depending on your data symbol, your signal may have low carrier frequency, high, low, high, high, low, something like that. And this change in frequency was easier to detect using very non-intelligent circuit long ago. So popularity of FSK was one due to the low complexity of your receiver. But now we may have much more complicated computation possible in our receivers, thanks to the advance in this left side building guys miniaturizing the circuits. So we develop better modulation schemes. That modulation schemes may require more computation, but now that computation is affordable. It's not costly. So we may kind of maximize our efficiency in spectrum use. So that is a kind of trend in digital modulation. So digital modulation schemes become complicated and complicated. So it's too complicated to be being taught in this introductory course. If you take a look at the OFDM, that is very popular and not only in Wi-Fi but also in cellular, in the first glance, you may not understand what's going on. Okay. And if you dig up more, actually, there is more complicated thing waiting for you. Why this is occurring? Because we now have very, very high computational power in our transmitters and receivers. So we may design a better algorithm to best utilize our spectrum, our power of not only the computation, but real transmission power of our handheld radio equipment. Anyway, so this is the link between, I've shown you a very small fraction, link between carrier modulation related with baseband digital modulation. But let me emphasize again, it is not all, okay? There are many more digital modulation schemes. One good thing is that many of them are no longer used, especially if you just look at the contemporary standards like Wi-Fi and cellular, they are all OFDM based. So probably one of your desire in the next digital introduction to digital communications would be understanding what is OFDM. And actually, if you understand OFDM, actually you understand a lot of other modulation schemes. Okay, chapter 9. So this is what I emphasized already. In digital communication systems, we usually have what? Source and channel and sink or destination. So here goes the channel. Here is the information source. And here goes the information sink or destination. And what do we want to do? We want to design two blocks. And this block not only interfaces the source and channel, but also it does some computation so that our source message can be better transmitted over this channel. And also this block not only interfaces channel and sink, it also does its best to perform reliable and secure communication. Of course, the work is separate, jointly designed by this encoder part and decoder part. Even though I said encoder and decoder, sometimes this part is called transmitter, this entire block is called transmitter, and this entire block is called receiver. And depending on the channel, your encoder and decoder may have RF components. For example, if channel is a vacuum like deep space communication, then probably the only method to do wireless communication is to utilize radio wave. Of course, be careful. These days, the SpaceX proposes to use visible light for communication, because in the space, if you have two satellites, then between these two, what? There is no atmosphere. Then your visible light-based signaling may transmit your digital symbol very far away without attenuation. One of the reasons why we do not use visible light in long-range wireless communications for land mobile communication is that our atmosphere observes the light wave. However, in the space, the attenuation is negligible, so they have inter-satellite link that is mostly based on visible light. Since thanks to the fast development of optical communication components, these optical components, which were usually much more costly long ago, is now very cheap. Still, it's expensive, but very cheap. So you also need to pay attention to the communication using light wave frequency of electromagnetic wave. But anyway, so suppose this source generates an acoustic signal, acoustic wave, but your channel is deep space like vacuum. Then the key inevitable component in your encoder would be what? Converting components that converts the acoustic signal to electromagnetic wave. So long ago, the transmitter had barely that kind of components. But now we have much more complicated processor here to do very advanced modulation and coding. Same thing happens here. If you receive radio wave and you must generate acoustic signal, this decoder or receiver must have the converter that converts radio wave to acoustic signal. But these days, not only that simple analog components, but also many digital complicated components are included in the receiver. This is a block diagram from the textbook. And this is not all, but this is one of the popular block diagram, assuming that we have some carrier modulation. So this is for radio transmitter. Why? Because we have this part. Ready? And this is radio receiver, means receiver that receives radio wave, because as we see here, carrier reference, right? And demodulation. Because modulation and demodulation are related to change the amplitude and phase of a carrier, which is usually real valued tone signal. Be careful. Now, due to the separation of modulation symbols and transmit pulse, sometimes, even though there is no carrier, people say modulation. However, here, specifically, you have carrier. So this is definitely for radio communication. So this is a block diagram for radio transmitter, and this is a block diagram for radio receiver. And this is the source. And we may say that this entire block is encoder or transmitter, right? Or including this source, you may say transmitter. And here we have separation of A to D converter and encoder. This may be further divided to source encoder and channel encoder. But this separation of these blocks or even this encoder block is actually arbitrary, even though it's very popular. As a future researcher, you do not confine yourself to understand that transmitter must consist of these components, because this is just for convenience. You may devise a new method to do encoding better. Got it? This is one of the reasons why we have this separation is just for convenience, because there is very good uniform sample, because there is very well developed channel encoder. But sometimes, depending on the channel, you have to devise this block entirely differently. One of the trends these days is that let's redesign this part based on the context or semantic of your communication. So currently, semantic communication is one of the interesting trends. And What they want to do is to redesign the encoder part and also the decoder part, heavily relying on the property of the channel and also what is to be done after we receive the information. Before estimating the information sent by the transmitter was important at the receiver. So if there is a bit sequence and you want to recover the bit sequence, now the trend changes. What you want to now do is this. There is some information, but not only recovering the information is important, but also taking actions is important in the receiver. It's like it's different from just watching a baseball game and managing the baseball game. Probably some of you are baseball fans and you watch a baseball game and say that, okay, next step would be something, 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 and this may occur. That is one thing. But the manager or head coach must decide what to do. So just sending information or estimating or predicting something to happen is not enough. You have to choose your best action, and best action itself also interacts with your next action. In that case, the conventional recovery of these symbols is not enough. So this semantic communication is one of the trend to do something more with our digital communication. Let's do some control actually. So now we combine the communication and optimal control theory. You may say that. So if you are interested in communications, also you must have interest in optimal control. If you have interest in control theory, I recommend you to have interest in digital communications because they are now being combined. Anyway, so these blocks are very important, but these are typical blocks. In the future, they will be obsolete. Okay. Anyway, so similar terms like we have ASK, PSK, FSK, QAM, many variants, OFDM, these waveforms, blah, blah, blah. Okay, what's wrong with the slide? It's not synced. Okay. Okay, what's wrong? Just a second. So we are now synced. So these chapters are all about digital communications. Some of the terms I already mentioned, and many of the terminologies will be taught in the next course, Introduction to Digital Communications. But now you understand some of them already. Here, coherent and non-coherent usually means you have whether you have recovered phase information or not in the receiver. Or in digital modulations, transmitter assumes the receiver is going to recover phase information or not. So if your transmitter and receiver pair, when it is initially designed, the receiver is not supposed to recover the phase, you must send information not in the phase, but just in the probably amplitude of the carrier, right? If you design the transmitter and receiver pair where your receiver will definitely recover the phase, then what do? You may put the information in the transmitter to the phase. So coherent and non-coherent separation is very important. And in between these two, we have differentially coherent. And differentially coherent modulation and demodulation scheme is based on this idea. Even though we may have difficulty in the receiver to recover the phase signal that will evolve as time may be a slowly varying signal. In that case, even though we may not track or find the phase, but the phase between two consecutive symbols may not vary a lot. In that case, we may assume the phase is fixed between two consecutive or three or sometimes four or some finite symbol periods, and we may exploit that information. By the way, the term exploit has some very objective meaning and subjective meaning. So in Korean, sometimes it is translated as 기회주의적인 or opportunistic. That sounds bad. And also in Korean, 착취적인, exploit. But here, as a very objectively, this means utilize or use well. So we may exploit the fact that the phase, even though it changes, but may not change that fast. We utilize that fact well and design some differentially coherent encoding and decoding scheme. And also here, the term synchronous and asynchronous here, usually A means not. Okay? And this synchronous, asynchronous is not usually about timing, actually. If timing of a desired signal, it's timing of unwanted signal or something. And some of you have seen slotted aloha in the introduction to communication networks. And in the original aloha, the received packets from different transmitters are asynchronous. However, in slotted aloha, we have some synchronism, not perfect, but some synchronism among the packets arriving to the receiver. In that case, we may call the original aloha as an asynchronous system and modified slotted aloha as synchronous system. However, in different time scale, still a slotted aloha may be viewed asynchronous. So this synchronous, asynchronous depends on the time scale of our interest. And here, the slide shows some performance metrics used in digital communications. The first thing is signal to noise ratio. And unfortunately, even though you've seen the SNR is defined in a very different ways. So be careful. There is no universal definition of signal to noise ratio. So whenever you talk about SNR with somebody else, first find out what is the definition of signal to noise ratio. Sometimes probability of error is important, but this has a lot of different definitions. Sometimes you have probability of bit error. Sometimes you have probability of symbol error. Sometimes you have probability of block error. That is sometimes called block error rate. There are many different definitions of probability of error. You may have probability of packet error. Okay? So always be careful. Also, unfortunately, there are a lot of different definitions of bandwidth. Bandwidth in real passband, bandwidth in complex baseband, strict sense bandwidth, root mean square bandwidth, some other bandwidth, 3 dB bandwidth, and there are noise band. There are many different definitions. Even these terminologies are not all covered in introductory digital communications. So it's almost impossible for me to even list up these different definitions. But what is important is this one. Whether it is analog or digital communication, we as an engineer usually does what? Optimization. So we formulate an optimization problem. And when you formulate an optimization problem, you have to choose your objective function. Unfortunately, there are many different performance metrics, among which you cannot choose just one. So strictly speaking, your optimization problem is multi-criterion optimization. You not only want to reduce the error rate, but also you want to reduce the complexity in the transmitter and receiver. You may want to reduce the power consumption of transmitter and receiver. So there are many important performance metrics. And more important is that these days, our wireless network, especially cellular networks, wants to provide many more different types of communications, like very wideband communication, very reliable communication, very less latency communication. These different types of communications requires different types of performance metric important in your optimization. So the system becomes more and more complicated. Fortunately, this complicated operation that definitely requires more computation power is now being available by the development of these electronic circuits. They are very fast, very small, very low power consumption circuits. So these two areas in electrical engineering evolves and stimulates each other for fast evolution of the communications systems. As I told you, I didn't cover much about the noise, the effect of noise in communication systems, because I promised not to talk about random variables and processes much. But let me just show this simple case. So here is a transmitter that have a NRG, and here you have some noise. What will be the output observed by the receiver? It may look like this. So sometimes see that here definitely the message symbol is at zeros. If you sample here, you may make an error. So what do? We do channel coding. So depending on the property of channel, we design an encoding method that is robust to channel noise. Then the question would be, how can we design such a code? That is the topic of entire channel coding course. If you look at our curriculum, then next semester in our master's or graduate level communications courses, you will find error control coding. That is all about channel coding to have robustness to the noise, something like that. Anyway, I will not cover them all, but as you see here, what is this one? Gaussian bell curve. You need definitely the prerequisite probability and random processes. Here you will see the performance metric probability of error, and usually this vertical axis and also the horizontal axis have log scale, and you have a waterfall like a curve here. What does that mean? In log scale, if you have straight line, that is what? That is a rational function, or well approximated by rational function. But it reduces much faster than any straight line with any slope. Then usually such a function, error probability has very small tail or so-called light tail. And when you have a light tail, then it's very hard to analyze the performance, but it also gives you fast diminishing error rate. Anyway, there are many topics to be covered in digital communications, error control coding, and also information theory, all related with probability theory. And again, this chapter also shows the matched filter. And the setting is slightly different, so don't be confused. I've given you the simplest matched filter definition, and here you have two signals for binary symbol detection. Anyway, I will not talk about this all. This shows a modulated signal by ASK and PSK and FSK again. You must be able to distinguish what type of modulation is employed by just looking at the modulator output. There are pages about FSK, pages about pulse amplitude modulation, pages about zero ISI condition again, and many other topics. So time is almost up, and next time, which is the Wednesday, the final class meeting before the exam, I will talk about this last part of our chapter 1, where some information theory related slides are there. So if you go down here, here goes the pages for information theory, Shannon's figure, and also the chapter 11's old edition, chapter 11, information theory and coding. So I will give you some very short preview of information theory in the next class meeting. It seems that we have 5 more minutes, and our clock says 10:47. Okay, let me continue more then. It will be very quick. So here, chapter 10 also talks about memory modulation and synchronization, and some interesting topics like spread spectrum, because direct sequence spread spectrum was used for 2.5G and 3G. And if you remember, 3G WCDMA actually employs this spread spectrum modulation. And among many different formats of multi-carrier modulation, OFDM is employed by what? Wi-Fi and 4G and 5G cellular communications. That's why our textbook tries to cover this spread spectrum and multi-carrier modulation part, but I will also defer the discussion, in-depth discussion, to the Introduction to Digital Communications course. So we will just see some figures like this. Here we have quadri, which means 4 phase shift keying. And QPSK may be understood in 2 different ways. One is what? One is simply just the phase may take 4 different values. Or you may convert that signal into the in-phase component and quadrature component, and view each components have real valued baseband signal to modulate the cosine carrier and sine carrier. So as I emphasized in this course, given the same mathematical formula, you may have totally different perspective. So, and this totally different perspective may give you how to implement more easily than before. So here we are using this idea. Here, suppose you have real part and let me use AI and AQ. And the imaginary part, then this can be written as what? Written as AI sub n p of t minus nt cosine 2 pi fct minus a sub qn p of t minus nt sine 2 pi fct. So QPSK modulation symbol has in-phase real part and the imaginary part. And real part goes to the in-phase component, and the imaginary part goes to the quadrature phase component. And you may establish this equivalence and utilize the first line to have this upper branch. Lower branch, I believe. Yeah, here goes cosine. So, and this lower component goes in this upper branch. And you see this minus sign here that explains this minus sign. Got it? So remember this. You must be very versatile in converting a formula into different forms, like Cartesian form or polar form. Sometimes polar form gives you a totally new idea of how to implement your transmitter, how to improve your amplifier, how to simplify your receiver, something like that. So when you understand some formula in communications course, also tries to find and understand other forms that is mathematically equivalent. Because understanding one formula may not be enough. Understanding more equivalent formulas gives you a more chance to devise something new and something that breaks through. Okay, I believe time's up, and that's all for today.